Bismillahirrahmanirrahim. Assalamu alaikum everyone. So today we will be having our 7th lecture and we will be discussing on minimization with K-maps, right? So these are the points which we will be going through. K-map, as we already had another approach for Boolean function representation, right? And now we will emphasize on K-map in this talk, and then the minimization, right? After the representation, you have to minimize to save the place, the number of gates, and so on and so forth, and then how we convert a truth table to a K-map, right? And then the number of steps which we have to follow, right? And then SOP representation, right? So these are the main bullets which we will be touching in this lecture, right? So let's start. So K-map is actually a way of representing Boolean functions, right? So as in one of our previous lectures, I mentioned that the Boolean logic, it has its roots in languages. Like in our everyday life, in our daily life, we normally talk about and, or, and we sometimes negate our own saying or something. We say something which is negating an expression or something like that, something like that, right? So this K-map, it has its roots on or it has its roots in pattern recognition, right? So what normally you do, you recognize a particular pattern, and on the basis of that pattern you try to represent first your Boolean function, right? And then you try to simplify, and that's the way of handling Boolean expressions by using K-map, right? So the advantage of using K-map is that it's easier, and you are following these steps in a predefined sequence, right? But when we are representing or simplifying the Boolean expression in another way, right? So then we don't have any predefined set of steps, right? Or sequence of steps, right? So here we have the advantage that we have the sequence of steps, and we can follow them in order to represent and simplify our Boolean expression, right? So here you can look that we have a two variable K-map over here, right? So you can see that on the horizontal axis we have y, so this is 0, 1, right? And on the vertical axis or vertical column we have x, and we have 0, 1. So here we have x0, and here we have x1, right? So you can have, so here we have both 0, so we have to complement them, so x bar and y bar. So here we have y1, but x is still 0, so x bar y, right? So here we have x1, and we have y0, so x will be x, and we will represent y with bar, right? And in this column you can see that we have both x and y 1, 1, so we will write xy, right? So this is the way out. So for example, if we have this minterms, right, m0, m1, so how we will represent them? So this is the counting 0, 1, right? So here we will place a 1 because we have m0, and here we have m1, so we will place 1 over here. And whenever we will represent in the Boolean function, what we will do, we will compute, right? So you can see that we have here x bar, right, in y bar. So here y is 1, so we will have x bar and y. So this is the expression, right? So, and this is the truth table representation. We already have gone through this representation, and this is unique, right? So we have a unique truth table representation. But as far as this Boolean expression is concerned, we can have a number of different representation regarding this Boolean expression. But the truth table will always remain unique, right? So we have two variables over here, so 0, 0, 0, 1, 1, 0, 1, 1 possible combinations x and y can have, and this is the f, or you can say this is the output. So 0, 0, 1, on 0, 1 we have 1, and 1, 0 we have 0, 0. So here we will have to place this one over here and then this one over here, right? So this is m0, this is m2, right? And this is the m0, m1, m2, and m3, right? Right. So this is a very simple K-map representation, right? And now let's move to the more K-map representation with more number of variables, because previously we have only 2 number of variables. So here if you have one variable, you can see we have a state horizontal line, right? And if you have 2 variables, we have this square sort of representation, 0, 0, right? And then 0, 1, and then 1, 0, and 1, 1, right? And when we move on and we switch to 3 variables, then you can see we have a cube over here, right? So the dimensions are increasing, right? So you can say this is a single dimension and this is the 2 dimension. As we can see, if n is 2, we have 2-dimensional representation. If n is 3, we have the 3-dimensional representation, right? So here you can see that we have 0, 0, 0, right? And then we have 0, 1, 0. And then we have 0, 0, 1, right? And then 0, 1, 0, right? 0, 1, 1, and similarly we will move here on the square, which is at the base of this 3-dimensional figure. So here we have another dimension, n is equal to 4, and this is, you can see that we have a cube, and then you can see that this can be considered as the projection of this cube. So you can see that it's a bit complicated. So imagine if you raise n to 5, right? If you have n is equal to 5, so this will become more complicated. So this is the only disadvantage we have. As we increase the number of variables, it becomes more complicated to handle. But on the software basis, we can handle those sort of different dimensions, right? So here we have the same scenario. We have 4-dimensional, you can say n is equal to 4, 4-dimensional representation, right? So, and we have to take care of certain number of steps, right? So as you can see that over here, each vertex, right, it represents a minterm. So you can see if you look at this, this is the vertex, right? So here you have 0, 1, 1, 1, and it represents a minterm, right? And then as I have mentioned that the complexity of this representation increases as you increase the number of variables, right? Okay, so then how we manipulate, right? If you have one dimension, then you can see that how we can concatenate those different boxes, right? So you can have this, right? And right, so if you have n is equal to 2, you can see that we can concatenate the neighboring boxes, right? And we can join them like that, right? But if you have n is equal to 3, then you can see that in addition to this sort of concatenation, we can also flip, right? So you can see this bend, right? So it means you can bend or flip them, right? So if you have a 1 over here at M2 and you have a 1 over here M1, so you can bend them so that you can have a right situation like this when you have two horizontal adjacent boxes, right? Moreover, if you have a 1 over here and 1 over here, you can again flip, or you can say bend them, and you can have the two boxes that are adjacent to each other, right? So when we have n is equal to 4, you can see the representation. We start counting from here, M0, right, M1, and then we move here. This is important, M2, M3, right, and then we have M4, M5, and then M6 and M7, right? So, and then while moving from the second row, right, to the to onward, right, so instead of moving here, we will move here, right? So this is the mechanism, and we have to follow. This is the methodology, and we have to follow, right? So here you can see M7, and we placed M8 over here, M9, and then M10, M11, right, and 12, 13, and 14, 15, right? And here you can see that we can flip when we have n is equal to 4. We can flip it horizontally. You can see bent over here. For example, if you have a 1 here and 1 here, and you want to join them in order to have simplification. So we will see in a couple of slides that how we simplify, but I'm just giving you an idea that if you have a 1 over here and 1 over here, then what you will do, you will bend them in such a way that this will be joined or concatenated, or you can have a scenario like this. If you have this, flip this. So, and moreover, if you have a 1 over here and 1 over here, right? So then in that case, what you have to flip them, right, or bend them in such a way that they are representing the same scenario, right? So you can have this sort of scenario, right? So let me give you another example. If you have a 1 over here, 1 over here, and 1 over here, and 1 over here, right? And what you have to do, first we will looking for the maximum number of squares that can be connected, or that can be adjacent. So if I flip it horizontally, if I bend this, right, over this, then what I will be having a scenario like this, right? So here I will be having M1, M3, and M9, M11, right? So we have a square, and we will be concatenating them, right? Okay. So this is the same scenario, like whenever you have different variables, right, and how you normally move on or handle, right? So here we have represented the variables, right? If you have three variables, so we have a x here, right, on vertical axis, right, or you can say in this column, and then we have yz in this row or in this horizontal direction. So you can see 0 0 0 1 1 1 and 1 0, right? So you can see that we have a 0 0 0 1 1 1 and 1 0, right? So you can see that we jumped from here to here, and then we move from here to here, right? So this is the methodology, or this is the rule, you can say, and we have to follow it, right? So here you can see that if we have a scenario like this, then we have only one variable. All will be cancelled out, right? So we have a square here. So here we have two pairs, 1 1 1 1. So you can see that we this y bar, z bar, y bar and z. If you take y bar as common, so we left with, so how we will be handling. So you can see here, right, like if we have yz here and x here, so what you can do, you can have this is x, right, because this is 1, and then we have x, y bar, z bar, right, and then we have this, right, plus x, y bar and z, right? So you can take common and you will see that you can have simplification, right? Okay, so this is another example, right? So here you can see that we have, if for example we have to make this pair, right? So this is the pair M5 and M7, right? So you can see that here we have x, y bar, z, right? And here we have x, y, z, right? So here you will add them, right? Because we are making the pair, and then you can take x, z as common, right? And you can have y bar plus y, right? And this is equal to 1, right? We already know that this is going to be 1, so we are left with xz, right? So this is the simplification. And then there is another question, right? You can see that when we move on, if you consider this row, then you can see that we are only varying one parameter, right? So it means that it's similar to the gray code sequence. So the reason is that whenever we will alter only one variable, so if we have this pair, right, so what we can have x bar, y bar as common, and we are left with z plus z bar, right? So you will be minimizing one variable, so z will be minimized, right? And if you consider this, right, so x bar, y bar, right, and x bar, y and z, x bar, y and z bar. So here you can see that we have x bar, y as common and z plus z bar. So you can see we are eliminating one variable as we move on. So if you look here, right, in this column, if you have one here, then what you will do, we will have x bar, y bar, z bar, right, and here we have x, y bar, z, right? So what you can have, you can take y bar, z bar as common, right? And we will have x plus x bar, right, inside the bracket. Like here we have y bar plus y. So here in this case we have x plus x bar. So this will be going to 1, and we are left with y bar and z bar, right? So this is the reason that the minterms are arranged in the gray code sequence, right? Okay. So these are some rules, general rules, right? If you have a one scare, right, like how if we flip this, right, this we have a pair over here and pair over here, and we flip them, right? If we I bend this column so that they can be joined together, so we have a scare here, right? So what we will be having, right? So we will be having two literals if we have a 4 scares. So here we have a 4 scares, and we will be having two literals. And if we have two adjacent scares, right? So here if we have a pair, so what we will be having, we have 3 literals, because as I have mentioned that one variable has to be eliminated because we are following gray code sequence of minterm representation, right? So here you can see if we have this 8 adjacent scares, so then we are left only with one literal, right? And if you have all 16 1, then we are left with one only, right? So this is the way out how you, if you have only one, like you have a 1 over here, right? So what you will be having, you will be having 4 literals. For example, if we have a 1 here, so what we will be having, we have a 1 over here, so what we will be having, we will be left with wx, right? And then if you look here, we have y bar and z. So we have wx, y bar, z, right? And these are 4 literals. So these are the general rules which we have to follow when we are handling or manipulating K-maps, right? And this is the example, and in this example you will have an idea about the region, right? So if you have a scenario like this, we have 4 variables over here, and you can see that if you have to represent this, right, 8 and 10, right? So what you have to do, or you have to flip, right, or you have to bend. So when we will be bending, so what we will be having, we will be having those adjacent squares, right? So you can see that we have a 8 here and 10 here, right? And there will be also a change, right? So we have a 9 here and 11 here. So this is 1, this is the 2, right? 0, if you start from 0, we have 0, 1, 2, 3. So this is a sort of torus, right? And you have represented the adjacent squares, right? Okay, and next we have the example, right? So we have to simplify this Boolean function. You can see that we have minterm representation over here. So this is the summation 0, 1, 2, 4, 5, and we have this minterm representation, right? So how we will be manipulating or handling or simplifying this? So you can see we have a 0, so we will place a 1 here, then we have a 1 here, we will place a 1 here, then we have 2. So as I have mentioned that instead of here moving here, or placing here as 2, we move here, this is the 2, right? Then this is 3, right? So we will be having 4, right? And this is 5, right? So 6 here, 7 here. So here, rather than moving here, we will move to the bottom row, right? So we have 8, right? And 9, right? And then 10, and then 11, right? This is 12, 13, and this is 14, and this is 15, right? So now we have to make look for. So first we will look for the quad, right? So because we can have the maximum simplification if we have a quad. So you can see that we have a quad over here, right? So this is the quad, right? So you can see that those variables w and x, they will be eliminated because we are following the gray code sequence, though they will be eliminated automatically, right? And we are left only with y bar, because if you look, y bar, z bar, and y bar, z, right? So you can take z as common and we are left with y bar. So you can see a y bar, right? So then you can reuse the ones that we already have used while eliminating or while considering, right, this quad, right? So here you can see that we have 1, 1 here, right? So you can reuse 2 ones from this quad and you can flip it vertically, right? So here you have a square, right? So you can see that we have w bar and z bar, then we have x and z bar, right? If we consider this, right, and so here we have x, right, and if you look at this column y bar, z bar, so here we have y and z bar, so you are left with z bar, so x multiplied by z bar, right? So this is the simplification, and you can see and you can look the benefit of using K-map, right? So this is another example, right? So you have to simplify this, right? So you can try it yourself, right? Okay, so then let's move to the 5-dimensional or 5-variable K-map, right? So you can see that it's a bit more complicated, so you cannot straight away represent on a piece of paper. So what we have to do, we first have to fix A. So we fixed A here, A is equal to 0, so what we have, and then we have BC, right, and DE. So you can see we have counting 0, 1, 2, 3, and we reach 15. So after 15, when we move to 16, we have to vary the A, right? And you can see that we have a BC, DE over here, and then you have place the numbers in the same fashion, right? So 16, 17, then 18, 19, right? So here 20, 21, 22, 23, and then we move from here to here, right? So here you can see that we have 23, 24, 25, 26, 27, and so on and so forth. So you can have the difficulty or FS or complexity as we move on from 4-dimensional to 5-dimensional, and if we go on, then we will have to have another methodology, like you can use software to handle more dimensions, right? Okay, so this is again the simplification, right? So here what is different, like if you can see that in this representation we have all ones, right? So here if you take the complement of this Boolean expression, because we can always take the complement of a Boolean expression, right? So what you have to do, you have to you have to look for places, right, that are empty, or boxes that are empty. So here we have this whole column, right, and we have this box. So you can place zeros over there, right, and this is the complement of this. So you can see that if you are taking the complement, you can also have the same methodology, like you will look for right, so you can join, or you can have those 4 adjacent boxes having zeros, right? So here you can see that we are left with CD, right, and then we have a square over here. So in a square we have 3 literals, so we have A, B bar, C, right? So this is the methodology or mechanism that if you want to take the complement and you are using K-maps, right? Okay, so this is another example, right? So you have to simplify this, right? So you can see that if you represent this, right? So here we have a Boolean expression, right? So this is sum of the products, right? And then you can have a complement, and that will be obviously the product of the sums, right? So this is another way out to handle, right, and to represent Boolean expression. So you can see that if you have a K-map and you will get the expression after simplification, this is the expression, right? And then you will, if you will take the complement, then we are actually taking POS, or product of sums. So here we have SOP, sum of the products, right? This is sum of the products form, and this is the product of the sum form, right? Okay. So let's define another terminology. What are the implicants, right? So here you can see that we have a K-map, right? So so here we have implicants with 2 ones. You can see that we have only 2 adjacent squares that are being paired. So here we have this, then we have this one and this one. So these are the implicants with 2 ones. Then we have implicants with 4 ones. You can say them circles, or maybe 4 adjacent cubes, right? So here and you can also have this, right? So these are 4 ones, or 4 adjacent ones. So these are the implicants with 4 ones, right? So then what are the prime implicants? So you can see that we have a square over here, right, with 4 ones, right? But these 2 ones, they are not being utilized, right, if you consider this square, right? And then if you consider after flipping or bending, we will have this square, right? So then you can see that these 2 ones, they are not being utilized, right, if you consider this square. And then if you look at this, right, then you can see that those ones, they are not being utilized, right? So these are the prime implicants, right? you can see if you consider this square, so what you will have, right? We are left with A bar, right? And then we are left with D, right? So A bar D, right? And if you consider this, right? Right? So we have B here, and then we have, this is C D bar, this is C bar D bar, right? So B D bar, so you can see this, and then we have A bar B bar, right? And then we have another term, essential prime implicants, right? So here you can see that we have A bar D and B bar D only, right? Sorry. So we have another terminology, essential prime implicants, right? So we have another terminology, that is essential prime implicants, right? So you can see that we have A bar D, right, and B D bar, right, and we don't have A bar B, right? So the reason is that this prime implicant, right? So let's have another terminology, essential prime implicants, right? So you can see that we are left only with two Boolean terms, right? So A bar D, right, or B D bar, right? So these are the essential prime implicants. So if you look, then you can see that why we don't have A bar B, because this A bar B is covered by other two implicants, right, prime implicants. So that's why we have not added it as, or we have not considered is an EPI or essential prime implicant, right? So then this is the example, and I have taken this from your textbook. So you have a Boolean expression, right? So you can see that we have a 0, 5, 10, 11, 12, 13, 15. So we will start 0, right, 2, 0, 1, right, 2, 3, 4, 5, so we have 5, and then 6, 7, 8, 9, right, 10, 11, so we have a 10, 11 over here, then 12, 13, and then 14, 15. So you can see that here we have essential prime implicants, right, and this is the you can say that this is the representation of this Boolean expression on K map. So here we have the essential prime implicants if we follow the definition or we follow the terminology, right? Okay, so then we can also have the Boolean expressions or circuits that have multiple outputs, as we can have multiple number of variables, right, or you can have multiple number of inputs. So similarly you can have a multiple number of outputs, and the best example is your adder circuit, right, where you have a sum and a carry, right? So here you can see that we have the outputs that are more than one, right? So here you can see that how we will be handling this. Here we have F1, right, F2 and F3, right? So we have to handle the Boolean expression or circuitry that having more than one outputs in a different way, like we will be using Lusky method, right? So if you look at here, right, so you can have multiple output minimizations, right? So we normally have to encounter the circuitry, or we have to come across the Boolean expression that is representing more than one outputs, right? So in that case, how we will be performing minimization using maps, right? So here we have to adopt a different methodology, right? So the name is McLusky, right? So you can see that we have F1, F2, and F3. They are actually representing the output or the output of a circuitry. So the best example that I can quote is your adder circuit. So for example, you have to add two numbers, right, or two variables. Then what we will be having as a result, we will have a sum and a carry. So you have two output and you have to handle them. So if you are using maps and you have to handle, so you can adopt another methodology, right? So you can look here that we have multiple outputs. So this is the F1, right, and this is the F2, and this is F3. So you can see that how you are handling this, right? Okay, and then we have another representation, that is XOR or NOR representation of your Boolean expressions, right? So you can see that we have a map over here, and what we will be doing over here or using here, we are actually considering the corners, right? And here we are using the offset, right? So you can see that we have ones over here, right? So we have a one over here and then one over here, right? So how, because this if you look back and you try to simplify by using what you have studied so far, so this is not possible, but you can have another mechanism. So this is a kitty corner, so you can see that we can have this. So you can calculate, if you look, we have here A, B bar, C, right? So here we have A bar, right, and B, C, right? So you can see that if you want to represent this expression, so you can straight away represent this by XOR, right? So A, this is the symbolic representation for XOR, A XOR B, then C, right? And then here you can see that if you don't have adjacent ones and they are in the same level, so you can again use another mechanism, or you can say rule, to represent those ones, right? So this is normally called offset adjacents, right? Because they are not lying with each other, so there is a gap, right? So you can use offset. If you look at the Boolean expression, so you can have A, B bar, C, right? So here we have A, B, C bar. So if you simplify, we will get this expression, and you can see that we have B, XOR, C over here. So similarly, these are the, so you have A, right, and B is XORed, or B XOR C, right? So this is the another way of representing. But if you have four variables, right, so these are 3 variables. If you have 4 variables, then you can see that we have this sort of representation, right? Here we have 1 1 and then 1 1. So you can always have offset representation, right? So this is the F2, right? If you look here, so we have represented this F2 like this, right? And then we have F3, right? So we can represent the Boolean expressions, right, over maps, and we can represent them by using XOR and XNOR, right? So this is another example. So here we have used offset, right? So you can see that the level, they are in the if you count from 0, then they are in the first row, right? So they are not lying to each other. There is a one empty box between them, so we will use offset adjacents, right? So you can see that if you compute, so you can see, right? So here we have, if you look at this, right, A bar, B bar, right? So C bar, D, right? So A bar, B bar, if you look at this one, and then C, D bar, right? And then we have to handle this, right? So A bar, B, and then C bar, D bar, right? So here A bar, B, right? C, D, right? So what you can do, you can take common A bar, B bar, right? So this is C, because we are left with C bar and D, and then CD bar, and that is, we always know it's a XOR operation between C and D, right? And if you look at this, right, so we will take common A bar, B bar, right, C plus, or XOR plus in a circle, right? So then XORed with D, but you can see that we have the complement, right? So you can have more compact form, and you can present this F1 by 2 XOR operations and 1 complement and 1 AND operation, right? So this is the simplification when we are using XOR, NOR, right, and using maps, right? It's so here we have another example. So we have, now we are using kitty corner, right? So you can see that we have 1, and they are at the corners, and you can represent them like this, right? A bar, B bar, if you look at this, right? CD, and then we have A bar, B, right, and C, D bar, right? And similarly, if you look at this corner, so we will be having AB, and then C bar, D bar, right? So here we have A, B bar, and then C bar, D bar. So you can see that we have 2 XOR and 1 AND, right? Okay, so this is almost the same. Now we are having the truth table, so you can have 2 variables, and then we are having 3 variables, right? So you can see that we have a truth table over here, and this is the output. So you can see that this is A, B, C, and you can represent this, right? So these are the examples that are taken from your textbook. So you can see that we have a Boolean expression 2, 3, 4, 5, and we have 3 variables. So you can have this sort of arrangement, Y, Z, right, on the horizontal axis, and on the vertical axis we have, or in the columns we have X, right? So we have 0 1 and 0 0 0 1. So this is the gray sort of sequence, right? So you can see that 2, so 0, right, 1 and then 2 and then 3 and then 4 and then 5, right? So you can see that we have this, right, this square and this square. So we are left with x bar y plus x y bar. Then this is another example, right, again from your book. So you have to simplify the Boolean expression, right? So we are m0, m1, m2, m3, right, 4, 5, 6 and 7, right? So we have 3 and then we have 4 and then we have 6 and 7. So you can see that if you flip, right, so we will be having this and this, right, and then we have this square also. So this is yz and these are xyz, right? And you are left with xz because you will be taking common xz bar, right, and we are left with y plus 5 bar, which is equal to 1, right? So this is another example, right? So you can see here we have this Boolean function, right? But you can see that we don't have, we have a bar c, right, then a bar b, then a b bar c, and then b c, right? So you can see that we don't have b here, right, we don't have c here, and we don't have a here. So what we will be doing, so I can do this, right? So if you look here, I have because this is 1, so I can multiply this b plus b bar, right? And then here we don't have c, so I have multiplied this expression with c plus c bar because this will be always 1. And then we have a b bar c, right? And then we have b c, and then here we don't have a, so what I did, I have multiplied this expression with a plus a bar, right? So you can see that after the multiplication, right, so we will be having this expression, Boolean expression, right? So you can see that we have a lot of same terms, similar terms, a bar b c, right? So it is repeated 3 times. So what we can have only one term, because this is the axiom or rule that we already know. So we can have one term containing a bar b c, right, and then this is a bar b bar c, right, and a bar b c bar, and then, right, so you can see this is the, right, and we always know that these are the minterms, and we will be having ones, right? We will place the minterms that are having ones, right, in this column. So here we have m1, so if you look, we have placed here, right, 1, then m2, yes, m2, m3, yes, m3, right, and then we have m5, right, so m4, 5, so we have m7, right. So if you simplify, we are left with c, right, if we consider this square, and if we consider this pair, right, so will be having a bar b. So this is the simplified expression, right. So you can see that we have a bar bc, right? A bar BC, if you try to look A bar BC, right? So we have 1 here, and A bar B bar C, right? A bar B bar C, so we have a 1 here, and then A bar B C bar, A bar B C bar, we have a 1 here, right? And then A B bar C, A B bar C, so we have A B bar C's, we have a 1 here, right? And then we have ABC, so this is ABC, and rest of the terms, they will be zeros. So these are the min terms. So you can look the advantage of using K-map rather than solving this, right? So here you can see that we don't have any sequence of steps. You have to multiply, and then you have to place the terms, similar terms, and then you replace them by using different Boolean axioms and laws, right? And then after that we even need more simplification, right? But if you use the K-map, right, so it is much more easier, right? So these are the rules, right, which we have to follow, right? And you can read them, right, because we have already applied them, right? So this is almost the same, right? So this we already discussed, right, why we are using gray code, because because you can see that we only have one alteration or one change. So from here to here we have 0 to 1, and then from here to here we have only 1 1 and then 1 0. So this is a sort of gray code, right? Because then we will be having simplification if we are considering those two adjacent boxes. Then what will happen, that B will be eliminated, right? So this is a sort of elimination, right? So these are the examples. So let's have this example, right? So we have a circuit over here that is a simple adder that normally add two numbers, right? So A and B, these are two variables, and then so here we have a C in, right? So you can say that this is the carry, right? And this is the C out. So this is also carry, but this is carry in, carry out, and this is the sum. So how we placed, so we have AB, and then we have the C in. So you can imagine that why we have this C in. If you look at this addition, right, so you will immediately realize that why we put C in over here. Then we have a sum over here, and this is the output, and then we have, this is the carry out, right? So if you look at here, this is, you have to add them. We got sum 1, right, and there is no carry, right? And then you move on, sum 1, 0, 1, 1, we always have 1, and this is 0, and then 1, 1. So here we have sum 0, but we will get a carry out as 1, right? So here we have a sum 1 and carry 0, right? So here 1, 1, right? So sum 0 and carry 1, right? So here we have 1, 1, sum 0 and carry 1. So here we have 1, 1. So we have sum 1, right, and carry also 1, right? So how we will be designing this circuit using K-map, right? So this is an adder, right? So but remember that this is only a 1-bit adder, right? So first we will be focusing on this sum, right? And we will look for the minterms that have 1, right? So here you can see we have a 1 here, 1 here, right? 1 here and 1 here, right? And then we will focus on C out, and we will look for terms or for minterms that has 1 in this in the corresponding position. So you can see we have a 1 here, 1 here, 1 here, 1 here. So if you look 1, right? So we will be having A bar, B, right, and C in, right? And we have a 1 here, so we have a second term, right? So A, B bar and C in, right? And here we have another one, so here we have A, B and C in bar, right? So this is the last one. So here we have A, B and C in. So this is the way out how we find the Boolean expressions for these two outputs, right? Okay, and now we have to simplify, right? So as I have mentioned that when we are simplifying by following the Boolean laws or axioms, we don't have any predefined number of steps. So here you can see that we have paired them, right? And we have taken common from them, right? So you can see that B, C in is common, carry in is common, so we are left with A bar plus A, right? So here we have A, C in common, and we paired them, so we have B plus B bar, right? So here we have C in plus C in, right? C in bar plus C in, so we have A, B common, right? And we have paired them, right? So and this is 1, right? This is also 1 and this is 1, so we are left with B, C in, A, C in and A, B, right? But if you use the K-map, right? So look, what we will be using, right? So we have C out, right? So we are actually focusing on C out, right? So you can see that we have, if you start counting 0, 1, 2, 3, right? So we have a 1 here, 0, 1, 2, 3, right? And then 4, 5, right? And then 4, 5, right? And then 6, 7. So we have 1, 1, and you have paired this, right? And then you have this pair, right? And this is another pair. So this is very simple. But if you look here, if you look back on your previous manipulation or simplification, then you can see that you have to go through a number of steps, but here you can straight away find out the C out, right? So then we will consider S, that is representing sum. So here you can see that we have a 1 here, right? So this is 0, 1, right? And then a 1 here, 2, right? 3, 4, then this is 3, 4, right? And then we have 1 here, right? So we have 1, 2, 3, 4 ones, so you can see that 0, 1, this is 2, and this is 3, and this is 4th one, and this is the 5 and 6, 7, this is the 7th one. So what we will be having, right? So there are no pairs, right? So no simplification. So it's your choice how you handle, but if you look at the carry out, you can simplify it quickly as compared to simplification by using Boolean algebra, right? So this is you can see that there is no reduction there because there are no pairs, right? And even if we use those sort of adjacent, right, offsets, then we can do something, right? But this is not the conventional K-map, right? So you can do it yourself because we have already an idea that how we will be handling the the ones that are not adjacent, right? So there is an offset, so we can say that this is a 0, there is a 0, there is an empty box in between these two boxes, right? So we can use the offset adjacents, right? Or offset adjacents, right? So, and similarly, if you look at this row, we have 1, then this is the empty box, this is also 1, so you can also use offset adjacents over here, and you can represent them by using XOR, right? So we will see that we can represent this sum by XOR operation, but by using offset adjacents, right? So this is all over for today's lecture, right? So and these are the points which we studied today, or these are the main topics, right? Like we have learned Karnaugh representation, that how we represent Boolean expression or truth table by using Karnaugh map. Then how we simplify the Boolean expression by using K-map, and then we have studied different number of dimensions, like if we move from 1-dimensional to 2-dimensional and 3-dimensional and 4th dimension and so on and so forth, and what are the complications when we raise the number of variables, and then we studied different mechanism of handling adjacent ones, right? You can say offset, right? And then corners, then how we handle those sort of ones, right? And we normally use other representations that are XOR or NOR, and we will be having more K-maps in our next lecture, but my recommendation is to exercise more and more so that you will be able to handle different scenarios and different examples. So that's all for today's lecture, and from my side, अल्लाह हाफ़िज़। अपना, अपने दोस्तों का, अपने रिश्तेदारों का, अपने गिरदोनवा के लोगों का ख्याल रखिएगा। अस्सलाम वालेकुम।